All right, let's do some homework. How's that sound?
Yeah, that sounds okay. I like homework.
Good. All right, chapter 3, number 1. What's the total mass in atomic mass units of carbon in each of the following molecules?
What does that mean?
Well, they want to know what of the total mass is being contributed by carbon. So if we use our periodic table to identify, remember, what mass carbon has.
Oh, I know. It has 12.
Okay, good. Yeah, so there's our mass right there, 12.0. That's fine. We'll use that 12.0. And then we can look at what total mass the carbon is in all of these molecules. Okay, so the total mass of this molecule, CH4, is the carbon plus the 4 hydrogens. But just from the carbon, it's just 12, right?
Oh, okay.
And then from this one, is that also just 12?
Yeah, I guess so.
How about this one?
Is that 12 times 12?
Yeah, because there's 12 carbons, right? So 144. Good. And then here, how many carbons do we have?
Oh, that's a tricky one. Do we have 5?
I think so. So if we count them there, 1, 2, 3, 4, 5.
Yeah, 12 times 5. Is that 60?
I think that's right. Okay, good. Very good. What is the total mass of hydrogen in these molecules?
Oh, now we're looking at the hydrogen.
Yeah, do you remember the mass of a hydrogen atom?
It's just like 1, right?
Yeah, it's 1.01, right? If you want to go 3 significant figures. So we'll do just 1. 1's fine.
Okay, so 4, 1, 10.
That's right. 4, 1, 10. And how many here?
6, 7, 8, 9, 10, 11, 12.
So it's 3 and 3 is 6, 7, 8, 9, 10, 11, 12. That's right. Good. So now we calculate the molecular or formula mass. What's the difference between molecular and formula mass? Fred, do you know?
Is that referring to whether it's a molecule or an ionic compound?
That's right. That's right. Molecular compounds, we can call it the molecular mass. If it's an ionic compound, it's not appropriate to call it the molecular mass, even though people do, and it's not that huge of a deal, right? But the formula mass is the way that we would refer to the molar mass of an ionic compound. All right, so let's find them out. How do we do that?
P4, where's the periodic table?
That's right. We need the periodic table. We need to find out what mass of phosphorus is. 31, it looks like.
Okay, so 31 times 4?
That's right. 31 times 4 because there's four phosphorus. All right, the next one.
Oxygen says there's 16, and hydrogen was 1, so that's at 18?
Very good. 18. That's the atomic formula. That's the formula mass for water. Also, you could call it the molecular mass because water is a molecule, right?
Yeah.
Okay, next compound is an ionic compound, right?
Yep, how's the metal?
Ionic compound. So we just have to add up 1 calcium. How many nitrogens do we have there?
2.
That's right. How many oxygens?
6.
That's right. And that's just for the folks at home, just in case there's any confusion. We'll talk a little bit about that. CaNO3, 2, like that. This 2 is meaning that I have 2 of these NO3s. They're nitrate ions. They have negative charges. And if you don't remember that, then you have to make sure you remind yourself by taking a peek at the polyatomic ion chart, these nitrate ions. Okay. And then calcium. There is 1 calcium. What's the charge on the calcium ion?
Looks like it's a +2.
That's right. I can tell because there's 2 nitrate ions and that it's a 2 plus. I can also use the periodic table because calcium is a representative element and its location, 20 electrons, showing that it wants to attain a noble gas electron configuration. You can lose 2 of those electrons and have a positive charge. All right, so now I just need the mass of all the different atoms in here, which is 6 oxygens, so that's 16 times 6, right? 16, again, is the mass of our oxygen here, right? Some people get stuck and concerned about significant figures, which is absolutely fine, but we can generally simplify and be okay. the number of significant figures we need, depends on the calculation we're performing. So when the time would come that we need to know exactly how many significant figures we want, then we could use that number of significant figures from the periodic table, right? If I know I needed 3, then maybe I take 5 significant figures here. Even if I took 5, it looks like it'd be 1, 2, 3, 4, 5, 15.999. That would be my 5 significant figures. All right. But yeah, so that's how you would identify. For now, we can just go 16 times 6 plus how many nitrogens?
2.
2 nitrogens. And it looks like 14 is a fine number for nitrogen. 14 times 2 plus what?
What's calcium?
Calcium. Let's take a look here to see what calcium is. It's 40. Okay, so we're going to be adding a 40. All right, calculator. Let's see what we get here. 16 times 6, 96. 14 times 2, 28. 40. So we got 96 plus the 28 plus the 40. 164 is how many atomic mass units there are in 1 unit of this compound. Do you know how to name that compound there, Fred?
Well, calcium and then the nitrates. Was that just calcium nitrate?
That's right, calcium nitrate. Good job. All right, next one here.
Oh, it's acetic acid, it says, right?
Yep, how many carbons?
2.
Looks like 2 carbons. How many oxygens?
2.
2 oxygens. How many hydrogens?
6.
Just 4, right?
Oh, 4. 4.
4 hydrogens. Is that everything?
I think that's everything.
Okay, so that's 2 times 12. I remember that. 2 times 16. That's for the mass of oxygen. And 4 times 1. So 24, 22, and 4. We have 4, 8, 9, 10, 0, 2, 4, 50. Is that what we're getting? 1, 2, 3, 4, 8, 9, 10. Yeah, 50 should be the atomic mass of acetic acid, or the molecular mass of acetic acid. Did I do that right?
I think so.
I didn't think that sounded right. That's supposed to be a 16, not an 11, so that makes that 32. There we go. So 16, 16 is 32, and that makes that 60. Okay, good. Next. All right, sucrose.
Sucrose, that's just table sugar, right?
Yeah. 12 carbons, so that's 12 times what?
12.
And then hydrogen.
22 times 1.
So 1 is the mass of a hydrogen, and there's 22 of them. Again, we're getting these from the periodic table, right? And then oxygen.
16.
16 is the mass of oxygen. How many are there?
11.
11. So 12 times 12, 144. 1 times 22, that's 22. 16 times 11.
I don't know what that is.
16 times 11 is 176. 176. So adding these together, 12, 4, 11, 12, 13, 14, 1. So 342 grams per mole for sucrose. Good. Okay, so now we want to do the same thing for these compounds given their structural formulas. And it's pretty straightforward, right? 1 carbon, 2 chlorines. What's the mass of chlorine?
Isn't it 35.45?
Okay, good. 35.45, so we'll go 35.5. Is that okay?
Okay.
35.5 times 2 chlorines and 1 times, or 16, this is the mass of carbon, chlorine, and oxygen. And this is the number of them, all right? There's 1, 2, and then 1. Okay, so 71, 12, 16, 109. Follow how we did that?
Yeah, that was straightforward.
All right, this one here.
That one's easy. 24, 26.
That's right, 2 carbons, 24, 25, 26. This one,
24, 26 plus the 2 bromines. What's bromine?
I think bromine's like 81. Right? Whoops. Where'd it go? Did I just close it? 80. 80 is bromine.
So 160.
That's right. So we have for this compound here, 2 carbons, 24, 2 hydrogens, 2, and then 160 for the 2 bromines. So 6, 8, 186 is the mass for 1 unit of that. All right. What do we got here?
1 sulfur, 4 oxygens, 2 hydrogens.
1 sulfur, 4 oxygens, 2 hydrogens. That's 2, 4 times 16 here, right? And this is 1 sulfur. Sulfur is around 32. We can double check here. And there it is, 32.1. We'll use 32. So 32, so 4 times 16 is 64. 32 plus 64 plus 2. And 4, 5, 6, 7, 8, 9. So 98 is our molar mass for, this is H2SO4, hydrogen sulfide or sulfuric acid if it's in water. Okay, determine the molar mass of the following compounds. How many carbons are on that system?
Is that 4?
That's right, 4 carbons. How many hydrogens?
8?
Very good. 3, 4, 5, 6, 7, 8. So C4H8, and that's 12 times 4 plus 1 times 8. So 48 plus 8, 56. And that's how many atomic mass units there are. It's also what we call how many grams there are per mole of that material, right?
Yeah.
Okay, here we go.
12 times 4 is 48, 49, 50, 51, 52, 53, 54 again.
54, not 56, but 54.
Oh yeah, 54.
Did we get 54 here? 1, 2, 3, 4. So this is 1, 2, 3. This is only 6. This is 3, 4, 5, 6. This is 8. Yeah, so this is 2 less.
Okay, and see there?
All right, how many chlorines?
4 chlorines.
Each chlorine was what? Do you remember?
Did we say it was 35.4?
Yeah, 35.5.
Okay, 35.5.
So 4 times 35.5. Silicon.
Can you have the periodic table over here?
Sure. 28.1.
28.1. 2 of them. And then 2 hydrogens.
All right, 2 hydrogens. So this is our what?
Chlorines.
Okay, chlorines. And this is our silicons, and that's our hydrogens. Okay. Calculator, 35.5 times 4. 28.1 times 2. And then 142 plus 56.2 plus 2. So about 200.2. That's our atomic mass. Okay,
What was phosphorus?
let's bring it up over here. 31. 1, 2, 3, 4 oxygens.
64 plus 31.
64. 31. 64 is for the 4 oxygens, right? 4 times 16. And this is for the 1 phosphorus.
And then plus 3.
Okay, plus 3 for what? The hydrogens?
Yeah.
So 4, 7, 8, 6, 7, 8, 9, 98.
Okay, looks good.
All right, which molecule has a molecular mass of 28.05? So we have 4 significant digits. So now we can use the 4 on the carbons, right? there's 4 on our, from our periodic, 4 significant digits from our periodic table. So with carbon, it's 12.01 if I use 4. We should actually bring in 5, 12.011. So that's going to be 24, 25, 26. So that's not going to be 28.
No.
This could be, right?
Yeah, 24, 5, 6, 7. That's probably it.
How about this one?
No, that's more.
Yeah. So our answer is going to be B there. And let's double check. Let's use the number of significant figures that they want, 12.011. Times what? 2. And then our hydrogen, we'll use 5 significant figures here. So we have 1.008. Whoops, 1.0079. That's 5 significant figures. All right, and then we have 4 of those. So we can use our significant figures here. 12.00011 times 2. Plus 1.0079 times 4. All right, 28.053. What were we looking to match? 28.05, yeah. Okay, good. Number 8. A mole of hydrogen, a mole of oxygen, and a mole of fluorine gas. What is the largest number of molecules? Which has the largest number of molecules? Explain why.
Well, I think this is a trick question.
What does that mean? What do you mean?
I think they're the same.
Okay, so if I have a mole of hydrogens, how many hydrogens, a mole of hydrogen gases, right? How many hydrogen molecules are there?
What's the number?
Oh, it's 6.02 times 10 to the 23rd. That's the chemist's dozen, right? You know what a farmer's dozen is?
You mean like 12 eggs?
Yeah. Do you know what a baker's dozen is?
Oh, is that like 13?
Yeah. And then a chemist's dozen is 6.02 times 10 to the 23rd. It's a much larger number. And we don't call it a dozen, we call it a what?
A mole.
That's right. It's the number that we use. Okay? So if I have 1 mole or that many of these, that's what I have. If I have that many of these, that's how many I have. And if I have that many of these, that's how many I have. So comparing those moles, which has the largest number of molecules, they're the same because they're all 1 mole, which is counting the number of them. Which has the greatest mass?
Is it oxygen the heaviest?
I think it's fluorine, actually, right? If you look here on the periodic table, oxygen is 16, but fluorine is 19. And that's just 1 fluorine, right? So F2 would be
19 times 2?
That's right, 19 times 2, or 28, 38, right? So this would have 1 mole of this would have the greatest mass. It would have a molar mass of 38. This one would be 16, 16, 32, and this one would be just 2. A mole of this would have a mass of 2, and again, I could say grams for every mole of it. So that's what we decided. We decided that we're going to put the units of grams per mole at the end of any one of these mass numbers. That's how many grams you have to get if you want to have 1 mole of that given material. All right, number 9. Which contains the greatest mass of oxygen? That many moles of ethanol, or that many moles of formic acid, or 1 mole of water, and explain why. Okay, so we're looking for which has the greatest mass. If I have 0.75 moles of C2H5OH, I can determine how many grams of oxygen, and what does it say? Which contains mass of oxygen. So it doesn't say oxygen gas, it's just oxygen. I memean, we can do O2 or O, as long as we do it the same for all of them, it doesn't matter, right? But from this, if I have that many moles of that material, I can convert that many moles of C2H3OH and relate it to just the moles of oxygen atoms, because there's 4 moles of oxygen atoms for every 1 mole of that material. And then for every mole of oxygen atoms, I could say I have 16 grams of oxygen atoms, right? So I have my 0.75 times 4 times 16, and that means I have 48 grams of oxygen in 0.75 moles of ethanol, okay? So I can do the same thing now for the 0.6 moles of formic acid. It's going to be 0.6 moles of the formic acid. I'm going to identify how many moles of oxygen there are in the formic acid. There's 2 moles of oxygen. Wait, there wasn't 4 moles of oxygen in here. That's just an OH. That's not a 4. Sorry, that's just 1. So it's going to be 48 divided by 4, which is just 12. 12 grams of oxygen for that first one. But 0.6 moles of formic acid, HCO2H, 0.6 times 2, because there are 2 moles of oxygen for every HCO2H. And again, 16 grams of oxygen for every 1 mole of oxygen. So this is going to be 0.6 times 16 times 2. 6 times 2 times the 16, and that's going to be 19.2 grams of oxygen. So this first one was 12. This is, 19.2. And the last one, water. There's 1 mole of water. This is going to be 1 mole of water. For every mole of water, how many moles of hydrogen?
Hydrogen or oxygen?
Or oxygen, how many moles of oxygen?
Just 1.
Okay. 1 mole of oxygen. And then there's 16 grams oxygen atoms for every 1 mole of oxygen atoms. Okay, so this is going to end up being just the 16. All right, follow that?
I think I got it.
Okay, so just a little recap. They had given us moles of some material, and they wanted to know how many grams of oxygen. And I can look at how many moles of the material there were given and compare that to how many moles of oxygen there were for every mole of material. And then compare that, moles of that oxygen, to how many grams that oxygen is, and identify how many grams of oxygen. Okay, good. Which has the greatest number of moles of oxygen atoms? Which has the greatest number of moles of oxygen atoms? All right. So a mole of the ethanol, a mole of the formic acid, or a mole of the water?
Well, that's kind of straightforward.
Why?
Because we know how many moles of oxygen there are in each one of those. And if we have a mole of each, then it's just that 1 times how many oxygens there are.
All right, good. Let's see if we can write that out to make sure everybody understands what you just said. But what you basically said, if I want to know, what goes to the right of my equal sign?
What do you mean?
Well, I want to know the number of moles of oxygen atoms, right?
Okay, yeah.
And I start with 1 mole of C2H5OH, right? And I can convert that to moles of oxygen by saying for every mole of C2H5OH, how many moles of oxygen do I have?
1.
That's right, 1 mole of oxygen. So if I have 1 mole of this, I'm going to get 1 mole of oxygen. I'll do the same thing with my formic acid.
It's going to be 2.
Can you see it already?
Yeah.
How can you tell?
Because there's 2 moles of oxygen for every mole of formic acid.
Very good. 2 moles of oxygen for every 1 mole. Time to go. All right, so we got a fire drill, we got a leave. Let me finish this one up really quick. Where is it at? HCO2H. HCO2H. There we go. So the answer is 2. Good job. And then the last one, we start with a mole of water, right?
Yeah. And then it's just 1 mole, right?
That's right. You can see that for every mole of water, for every 1 mole of water, there's 1 mole of oxygen. Therefore, the number of moles of oxygen is going to be 1. Okay? So, which contains the greatest number of moles of oxygen atoms? If I have 1 mole of this, 1 mole of this, 1 mole of this, the answer is this one because there's more of it, right?
Okay.
Now, hopefully you can see that if I'm talking about a mole of this, inside there are numbers of different things. This is C2H5OH, right? You can kind of think of it like a cookie. There's cookies, there's some chocolate chips, there's maybe some walnuts or whatever, right? So cookie, C, chocolate chips, H, walnuts, O, right? So I can identify how many chocolate chips there are in for every cookie. So a lot of people get bothered by how can there be 2 moles of water if you just start with 1 mole of the material, right? But if I start with a dozen cookies, I'm not going to have a dozen chocolate chips. I'm going to have, if there's 3 per cookie, I'm going to have 3 dozen chocolate chips. Okay? Does that make sense, Fred?
Yeah, I think I got that.
Okay, good. All right, number 12. Calculate the molar mass for each of the following compounds. Hydrogen fluoride.
Fluorine was 19 and hydrogen's 1.
Okay, fluorine 19, hydrogen's 1. If we look at fluorine, we see that it's 19 or 18.99, so that's close enough to 19, right?
Yeah.
Okay, so 20 there. Ammonia.
Nitrogen's 14, hydrogen's 1 each, so that's 17.
All right, good job. And that's again, ammonia, NH3, is 17 units, grams per mole. That's how many grams of ammonia you'd need to have if you wanted to have 1 mole of ammonia gas, right?
Yep.
All right, nitric acid.
Oxygen is 16, right?
Yep, so 16, 3 of those is what?
Is that 48?
I think you're right. And then what?
1 nitrogen, that's 14, and then a hydrogen.
All right, so 16 times 3 plus the 14 plus the hydrogen plus the 1.
Okay, 63.
Good. Silver sulfate.
Silver. I don't know silver.
I think it's 107. 107.8. So 108 is what we'll use for silver. So how many silvers do we need?
Oh, 2.
All right, good. And then SO4. So 108 times 2. That's for our silver. Sulfurs.
Just 1, and that's 32.1.
All right, so we can do the 32 probably. We'll get okay with just that many significant figures. Oxygen.
4 times 16.
Very good. 16 times 4. All right, so bring in our calculator. $312.
Is that right?
So, this is all practice for understanding what the atomic or the molecular or formula mass means, right? It's really easy to go on Google and just say, what's the molar mass of silver sulfate?
The molar mass of silver sulfate is 311.8 grams per mole.
Okay, so, and that's how generally you're going to be doing things if you want to know the molar mass of something, okay? So, but that's an easy way to double check as well. Boric acid, 1 boron, 10.8, 3 oxygens, 48, 16, 16, 32 plus 16, 48. So 48 plus 11 plus 3. Oh no, yeah. 48 plus 11 plus 3. 62. And then we'll double check here. molar mass of boric acid? All right, good.
The molar mass of boric acid is 61.83
Okay.
grams per mole.
Number 13. Good job, Fred.
Thank you.
All right, number 13. Calculate the molar mass of each of these things. S8. Sulfur is what?
32.1?
Yeah, 32.1, and then we just multiply that by 8, right?
Yeah.
Okay. C5H12.
5 12s and 12 ones.
Very good. So 13 12s, right?
Yeah.
Um, what is that compound?
SC, is that scandium?
Yep.
Sulfate?
Yep. Are you good with the sulfate ion?
Not as good as I could be.
All right. So let's bring it up here and take a look at it here.
There it is, SO4 2 minus.
Down here?
Yeah.
Okay. SO4 2 minus. Good. So scandium sulfate, is that the correct name?
I think so, right?
Yeah. It's polyatomic ion, just the name of the metal and the polyatomic ion at the end. Good. 2 scandiums. How many sulfurs?
3?
And how many oxygen?
12.
Very good. So just a quick review of that. SC2SO4, that's our other ion, and there's 3 of them. So there's these 3 of these SO4 2 minuses, right? SO4 2 minus, SO4 2 minus, 2 scandium. What's the charge on the scandiums?
The total charge on the sulfate's -6, so it must be +3.
Very good. Each sulfur has to be each scandium has to be a +3 so that it can compensate for the 3 minus 2s on 3 sulfates. Good. So what's scandium?
Bring up the periodic table.
There it is. 45. 45.
2 times 45?
That's 90, right? So that's our 2 scandiums. Sulfur.
Was that 32?
Let's bring it up here real quick. 32.1.
Okay, 32.1.
Or 32 would be fine. So 32 times what?
3?
3 sulfurs. Oxygen, how many?
12?
Yeah, there's 12 oxygens, which are 16. Okay, so adding those together, 90 plus 3 times 32 plus 12 times 16. 378 for scandium sulfate. All right, let me go over here. What's the molar mass for scandium sulfate?
The molar mass of scandium sulfate is 378.1 grams per mole.
Okay, so we got 3 decimal places correct, 378. Good job. All right, acetone.
3 carbons,
Okay, 3 carbons,
6 hydrogens,
6 hydrogens.
1 oxygen.
All right, so 1 oxygen plus 3 carbons plus how many hydrogens?
6.
Plus 6. So 58 acetone. Molar mass of acetone.
The molar mass of acetone is 58.08
good.
grams per mole.
I know this one by heart. Glucose. What is it?
6 carbons,
6 times 12.
6 oxygens,
6 times 16.
and 12 hydrogens.
12 times 1. So 6 times 12 plus 6 times 16 plus our 12. Okay, 180 grams per mole. Good. So that's how many grams you need if you want to get a mole of glucose. So if we're going to perform a chemical reaction with glucose and we want to weigh out a mole of it, we need 180 grams of the glucose. Okay, 16. Determine the number of moles of a compound and the number of moles of each type of the atom in each of the following. Okay, good stuff. So if I have 25 grams of propylene, C3H6, how many moles of propylene? How many moles of C3H6? All right, that's the question. Do you understand that?
Yeah, so if you have 25 grams, how many moles?
That's right. So to do this, I start with what they gave me. What did they give me?
25 grams.
25 grams of the C3H6. And then I want to go from grams of C3H6 to moles of C3H6. And I knew I wanted to do that because I know that I'm wondering how many moles. I can find out how many grams per mole by adding them up or saying, what's the molar mass of propylene?
The molar mass of
42.08.
propene is 42.08 grams per mole.
Let's see, did they say propene or did they say propylene? What did they just say? I said propylene. Yeah, that's right. Okay. C3H6 42.08. All right, good. I guess the idea is, oh, propene. One propene is another name for propylene. Okay, so what number was it again?
48.
Was it? Let me double check here. 42.
42.
42.08. So 42.08 grams for every mole. So I can see the math tells me that I need to take the 25 and divide by the 42.08. All right, so that's going to be 0.59. We have three significant figures here, 25.0 grams, so I want 0.594. That's my answer there, and the correct number of significant digits. Moles of propylene, that's how many I have. All right, 3.06 times 10 to the third minus 3 grams of the amino acid glycine. What goes to the right of my equal sign?
Moles of glycine.
That's right, I'm after moles of glycine, C2, H5, and O2. And I'm starting with 0.00306 grams of, I'm just going to call that glycine. All right, and I can go from grams of glycine to moles of glycine with the molar mass. I'm going to ask Google, molar mass of glycine.
The molar mass of glycine is 75.07 grams per mole.
75.07 grams per mole. Now, if I was on an exam, I would have to add up 2 carbons, 5 hydrogens, 1 nitrogen, and 2 oxygens. All right, so we got 75.07. Most of the time in the exam, however, they're going to also give you the molar masses as well. All right. Okay, so 0.0036 divided by my 75.07. Okay, so we have 4.08 times 10 to the minus 5. 3 significant digits, started with 3 significant digits. Follow that?
Yeah, I got it.
All right, 25 pounds of herbicide. Treflan? Treflan? Let's see if we can find the molar mass of Treflan. Molar mass of Treflan?
Here is information from ChemVK.
Okay, is that the same stuff? C13, H16, N2O4F, and 3O4F3. So, not quite the chemical formula that they gave us. C13, H16, N2O4F. There it is. So this one here has a molar mass of 283.275. 276. All right. So I want to know how many moles of TRE, I'm going to call it, or moles of tree. And I'm going to start with what? What did they give us?
25 pounds.
25 pounds. I'm going to give myself a little bit extra space because I need to go from pounds of TRE to, and they gave me a conversion factor here, grams, right? So 1 pound is 454 grams. All right. And then I can go from grams to moles. TRE, TRE. And the number again was, I wrote it down over here, 283.276 for every mole. Okay, so 251 times 454, going from pounds to grams, divided by 283.276, and that should be how many moles? So I got 402 moles of TRE. So 251 times 454, that's how many grams I had. And then divide by 200 again. So yeah, I got 400 and something grams. Good, that's right. All right, D, 16D, 0.125 kilograms of an insecticide, Paris green. All right, I will be using this to determine the molar mass of Paris green today. What is the molar mass of Paris green?
The molar mass of Paris green is 1,013.79 grams per mole.
Okay, so let's double check that. Whoops. That's the right chemical we're looking for. C13. Oh, no, sorry, this one. CU4. CU4. AS2. No, that's not the same stuff, is it? CU4. This chemical formula might be it. CU4. AS03. No, not the same. Well, you know what this means?
Are we going to have to add it up?
I think so. We're going to have to add it up. Okay, so we'll see how close we are. Maybe we're missing something here. Should be about 1,013 apparently. But all right, so 4 coppers. What do we got?
Is that 10 oxygen?
Let's see. There's oxygen right here. There's 6 there and 4 there. Okay, yeah, so 10 oxygen. What else?
2 arsenics?
2 of them? What's this? 10 oxygen, not 10 fours. 2 arsenics. What else?
Is that 4 carbons?
So 1, 2 carbons in there, and then times the 2. Okay, so 4 carbons. And what else?
6 hydrogens.
6?
Yeah.
Okay. Let's add it up. 16 times 10, that's 160. Oh, these are arsenics, 2 arsenics. Bringing out the periodic table here for arsenic. 75. 75 for the arsenic. 4 times 12, that's 48. 6 times 1, that's hydrogen 6. Let's find out what the copper is. 64, about 63.5. Oh, but there's 4 of them. Okay. Let's see what we get. 4 times 63.5, right? That's our first one, 254. Plus the 160, plus the 75. 175. 275 or what? Oh, there's 275s? Oh, there's 275. Arsenic is 75. Yeah, that's right. I have 2 arsenics. Sorry about that. I have a helper student here with me.
Who's that?
She's over there.
Okay.
So 2 75s plus, what else? 4 12s, that's plus 48, plus the 6, 618. That's a lot smaller than anything else was telling us.
Well, let's see. Did we do it right?
10 oxygens, that's 16 times 10. Yeah, that's right. 2 arsenics, 75 times 2. 4 carbons, 1, 2 times 2, 3, 4. 4 coppers, 4 times 63.5, that's the 254. And then 6 hydrogens. 618 grams per mole. So if we start off with 0.125 kilograms, and we would like to know how many moles of this Paris green we have, if I have 0.125 kilograms of Paris green, I can go for, what can I do here? I'm in kilograms and I want to get to moles. I know grams per mole, so I can use this conversion factor, 618 grams for every 1 mole of Paris green, right? But I have this in kilograms.
Just convert that to grams.
Okay, so kilograms down here, grams up here. 1,000 grams for every kilogram, like that?
Yeah.
All right, and then 618 grams for every 1 mole of my Paris green. Okay, so the 0.125, sorry, 0.125 times 1,000 gets us into grams, divided by 618. So 0.202 moles of Paris green. Okay, I'm concerned about that answer because the Paris green molar mass is significantly different than all of these Paris greens. But that's the chemical formula they gave us, right?
Yep.
Okay. 325 milligrams of aspirin. Aspirin. Molar mass of aspirin?
The molar mass of aspirin is 180.16 grams per mole.
Now I want to double check the chemical formula here. 6, 7, 8, 9 carbons. Hydrogens 8, 3, 4, 5, 6, 7, 8. Oxygens 4, 1, 2, 3, 4. Okay, so that looks good. So 180.158. That's good. So I can go to moles of aspirin. I can solve for moles of aspirin by starting off with 0.325 grams of aspirin.
No, 325 milligrams.
Oh, sorry, I did that in my head. I went from milligrams to grams in my head. I'll do one where I start with 325 milligrams of aspirin as well, going to moles of aspirin. But if I want to go from milligrams of aspirin to grams of aspirin, 1 gram has 1,000 milligrams, right? And now I'm in grams of aspirin. I can go grams to moles of aspirin. It was 180.16 grams for every mole. Here, I know grams of aspirin right off the bat because I did it in my head, just went from milligrams to grams. I can just go 180.16 grams of aspirin for every 1 mole of aspirin. Okay, good. So 0.325 divided by 180.16. So 0.0018, 0. That's 3 significant figures. Minus 1, 2, 3, minus 3. So that's how many moles of aspirin. Good. Let's do this one down here. 325 divided by 1,000 times, or no, divided by 180.16. Again, same number. Okay, way to go. That's number 16. All right, determine the mass of each of the following. So now we're given moles, and we want to know the mass. So if I have 0.0146 moles of KOH, and I want to know how many grams of KOH, how would I do that?
Grams to the right of the equal sign?
That's right. Grams of KOH is what I'm after. And I'm starting with here moles of KOH. Zero 0.0146 moles of KOH, and I go from moles of KOH to grams of KOH. Hold on. All right, so we're taking 0.0146 moles of KOH, and I need to get the molar mass of potassium hydroxide. That's what this stuff is, right?
Yep. Molar mass of potassium hydroxide.
You can never understand your voice, Fred.
Why not?
I don't know. Molar mass of potassium hydroxide. See? You got to say it like
The
that.
molar mass of potassium hydroxide is 56.11 grams per mole.
56.11 grams for every mole. So this time I'm taking the 0.0146 and multiplying it by the 56.11. All right, so 0.819 grams, 3 significant digits, and that's correct. All right.
10.2 moles of ethane.
All right, 10.2 moles of ethane. I would like to know grams of ethane. I'm starting with 10.2 moles of ethane. I need moles of ethane on the bottom and grams of ethane on the top. So grams per mole, 1 mole is how many grams? Molar mass of ethane.
The molar mass of ethane is 30.07 grams per mole.
Times 10.2. So 306.7, 307, 3 significant digits, grams of ethane. Okay, good. So 1.6 times 10 to the minus 3 moles of sodium sulfate. So 1 mole of sodium sulfate.
What's the molar mass?
Molar mass of sodium sulfate.
The molar mass of sodium sulfate is 142.04 grams per mole.
Grams per mole. Times the 0.016. We got 142.04 times 0.0016.
Showing pictures that match.
That didn't work. Okay, 0.227. And that's grams of sodium sulfate. Okay. Glucose. Do you remember glucose?
I do. It was 180.
Good job. That's how many, excuse me, that's how many grams there are per mole. So I would like to know how many grams of glucose. Starting off with 6.854 times 10 to the third moles. So 6,854 moles of glucose. Every mole of glucose is 180 grams of glucose. So 6,854 times 180. How many significant figures?
Just 3.
So 1.23 times 10 to the 6 grams of glucose. A lot of glucose.
Yeah.
All right, 2.86 moles of this stuff. Cobalt ammonium chloride. Cobalt ammonia chloride? All right, so we have to figure out the molar mass of that. 2.86 moles. I'm going to call it cobalt compound. And I would like to know how many grams of the cobalt compound, right? Each mole of the cobalt compound has a mass of, there's one cobalt. There's how many nitrogens?
6.
6 nitrogens.
18 hydrogens.
18 hydrogens.
3 chlorines.
3 chlorines. Cobalt, 59 grams per mole. Six nitrogens, that's 14 times 6. $84. 18 hydrogens, that's 18. Chlorine is 35.5 times 3. 106.5 plus 18 plus 84 plus 59. So 267.5 grams for every mole times the 2.86. 2.86 is how many moles it says it had, right? Okay, so we got 765 grams of cobalt compound. All right, good. Number 18. Determine the moles of the compound and determine the moles of each type of atom in the following. Fun, fun, fun. 2.12 grams of potassium bromide. Molar mass of potassium bromide, right?
Yep.
Molar mass of potassium bromide is?
The molar mass of potassium bromide is 119 grams per mole.
So if I have 2.12 grams of potassium bromide, and I need to get to moles, I go 119.0 grams of potassium bromide for every mole of potassium bromide. So that's how I'm going to stay in grams. Oh, no. I don't want grams, I want moles, right? Determine the moles, yeah. Determine the moles. So I'm going from grams to moles. So 2.12 divided by 119. And that's how many moles of potassium iodide, 0.0178. And that's also how many moles of potassium I'd have, and that's also how many moles of iodine I'd have. Because for every mole of this, there's 1 mole of potassium and 1 mole of iodine. It's different for the next one, though, right? 0.1488 grams of phosphoric acid. Grams of the phosphoric acid. We'll call it pH there. And I want to know how many moles of the phosphoric acid. To find the molar mass of phosphoric acid, molar mass.
The molar mass of phosphoric acid is 97.99 grams per mole.
So 0.1488. Double checking here, yeah. 4 significant digits divided by 97.99. That's how many moles of phosphoric acid, 0.001519. 4 significant digits. Now, the number of moles of phosphorus is the same as the moles of phosphoric acid because there's 1 mole of phosphorus here, right? For every mole of phosphoric acid. So I have 0.001519 or 1.519 times 10 to the minus 3 moles of phosphoric acid. But I have 3 times that many moles, that times 3 moles of hydrogen, and 4 times that many moles of oxygen. Okay, C, 23 kilograms of calcium carbonate. So if I start off with 23 kilograms of calcium carbonate, and I would like to know how many moles of calcium carbonate that is, right?
Gotta go from kilograms to grams,
Good. Kilograms to grams, and then what?
grams to moles.
You want to try it?
I'll try. Molar mass of calcium carbonate.
The molar mass of calcium carbonate is 100.09 grams per mole.
Good job. And there's 1,000 grams for every mole or kilogram. So 23 times 1,000 divided by 100 should be about 230 moles of calcium carbonate, right? 23 times 1,000 divided by 100.09. So we got 230. Three significant figures? Just two significant figures. So 230, yep, moles of calcium carbonate. Okay. Good. D, 78.452 grams of aluminum sulfate. All right. So I want to go from grams of aluminum sulfate. I'll call it just aluminum compound like that. 78.45. I want to go to moles of the aluminum compound. All right, so I need to know how many grams there are in a mole of our material. Okay, aluminum sulfate, molar mass of aluminum sulfate.
The molar mass of aluminium sulfate is 342.15 grams per mole.
Did you notice how they called it aluminium? Aluminium. The person who was given the opportunity to name aluminum did so at the time at which platinum was very popular and was emerging as the most valuable metal. Platinum. And they wanted to make aluminium sound like platinum. And so aluminum was not the sound that they wanted. They wanted it to be aluminium, so it sounded like platinum. And when aluminium came out, or aluminum, I don't mind what you call it, but when it came out, it was extremely popular. And it was very valuable, even more. I'm not sure if it was more valuable. I think it might have been more valuable as platinum. In fact, the top of the Chrysler building was made of aluminum, which was extremely expensive, and people were so impressed and surprised, amazed by it. However, as the cost to create pure aluminum came down tremendously, aluminum became very, very inexpensive, and it no longer became very valuable. And so people look back now and say, why did they use aluminum if they wanted to make it fancy? Right? But anyways, just a little bit of history there. And the Google calling it aluminium is not just a British accent. It's also a preferred pronunciation in somebody's, in many people's, I don't know about many, but enough people's minds. 78.45 divided by 342.15. That's going to give me 0.4 significant digits, 2293 moles of the aluminum compound, and that times 2 moles of aluminum, because there are 2 aluminums for every aluminum sulfate. That number here times 3 for the sulfur and times what for the oxygen?
12.
Yes, I need to take that number. That's how many moles of aluminum sulfate there are, times by 12 for how many moles of oxygen that we have there. Okay. 0.1250 milligrams of caffeine. I would like to know how many moles of caffeine. All right. 0.1250 milligrams of caffeine. What do?
You have to get the grams.
That's right. I need to go from milligrams of caffeine to grams of caffeine. What's the ratio?
1 to 1,000.
1 gram for 1,000 milligrams?
Yeah.
Okay, now I'm in grams of caffeine. And now I just need to go to moles of caffeine. What's the molar mass of caffeine?
The molar mass of caffeine is 194.19 grams per mole.
Okay, so 0.125 divided by 1,000 divided by 194.19. 4 significant figures. 6.437 times 10 to the minus 7 moles of caffeine. So I only had 5 significant figures there, but I think I should be okay. Okay, good job.